Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue the discussion on numerical integration. In the last lecture, we talked about memoization of integration. What it meant was that if I'm trying to calculate the integral function of a given function f, so I'm basically trying to calculate the integral from a to some point t. I want to calculate at different t's, right? So g of t is the integral function of f. And we said that a very good approach and a very fast and accurate approach is to use memoization. It means that if I want to calculate at some point t2, calculate this integral, and I have already calculated from a to t1, where t1 is less than t2. I can reuse that value and just only calculate the integral from t1 to t2. And if this delta t, basically distance from t1 to t2, is small enough, I can use a 3-point or 5-point gauss-legendre method to calculate this extra integral accurately, and then add the previous result to get an accurate result for t. And this helped basically get rid of the problem with the fact that when t goes very large, let's say t goes 100 times a, right? Then numerical integration, if we directly try to numerically integrate that large interval, we have to have a lot of sub intervals, which is not good. But this way of doing the calculation takes care of that, because we always just do the integration over a small interval and add it to the previous one. And the point here is that we want the value of g at all those points, not the end of the interval, all the points, right? And one good example is calculating convolution integrals. So a convolution integral appears all the time when you're studying linear time invariant systems, usually in linear control theory. So in the control theory of systems, convolution happens all the time. And it's basically based on the idea is that if I have a LTI system, linear time invariant system, I can characterize it with a function called impulse response. So this g of t, it's the impulse response and it's the characteristic of the system. It doesn't have any relation to the type of input that we put. And if I know the g of t, the impulse response of the system, then the output of the system to any given input f of t is the convolution of f of t with g of t. G of t being the impulse response, right? So f is the input, g is the impulse response, and f of t convolution with g of t is the output of the system, or the response of the system to the input f. All right? And that's defined by this integral, minus infinity to plus infinity, f of y, g of t minus y, dy. So y is a dummy variable, is the variable of integration, and g is the output. So this output depends on the variable t. So in this integration, t is fixed. We are integrating over y. And this, we can also write this in another form, in which f, the argument of f is t minus y, and the argument of g is y. And we are integrating over y, right? Both of these are equal, and they are basically the same definition for the convolution, okay? So if we have this LTI system, and if I know the impulse response, then I want to find the value of the output over time interval from time 0, for example, where I input the f of t. Let's say I apply f of t at time 0. And then I want to plot the response from 0 to t0. Let's say I want to find the value of the output, or this convolution integral, in 1000 points from 0 to t0, okay? So the naive approach again is that for each t we calculate the integral, we do a simple integration. The professional approach is that, okay, if I know the value of output at some point t, then the result is at another time step is the previous step plus some additional term, right? So we use memoization technique for fast and accurate evaluation. Now, an example that I put here is the low-pass filter. So a low pass filter, when we talked about filters, we typically present them in the frequency domain. So if we take this impulse response and calculate the Fourier transform of it, and this is just the magnitude. Low pass filter is pretty much flat up to some frequency, and then it starts to decay, all right, in frequency domain. In time domain, before t0, when we have before t0, it's basically 0, g of t0, and after t0, it's an exponential function, all right, and e to the minus t over tau, and tau is the time constant of the system, which is related to this flat bandwidth, flat frequency, right, this edge. And the amplitude of gt, so at t0, gt should be how much should it be? I believe it should be tau or 1 over tau, one of these two. And then in order to test for that, we can just look consider the Fourier transform of this. So Fourier transform of e to the minus t over tau times the unit step, because this is 0. It's 1 over j omega minus 1 over tau, right? Or 1 over j omega plus tau, plus 1 over tau. So it's and then if we want this to be normalized, so let's say the frequency response is normalized at 0 frequency, we get 1. So at therefore at time 0 we should get tau. Okay, so the amplitude of the response is tau. So the function is tau times e to the minus t over tau. Okay, so that's our impulse response, and it's 0 before time 0. And then let's say we want to calculate the step response, which means I want to put a step from 0 to 1. Okay, and therefore f is 0 before time 0 and f is 1 after time 0. So if we put if we use this one for calculating the output, the convolution, so if y is greater than t, it means that the argument of f is negative, which means f is 0. So the upper bound is limited to t when we are integrating over y. And then g of y, if y is less than 0, g is 0. So the lower bound is also limited by 0. So the output response for the step response is integrating of g, just the impulse response, from 0 to t. Okay, and the output is a function of t. So this is exactly the way what we talked about in here for memoization. So right, we're calculating the integral function of the impulse response. And note that if f was some other function than constant, it doesn't matter. The bounds of the integration are still 0 to t. But we get g of y times f of t minus y, right? For y less than t, or when the argument of f is positive. Okay? But here we're just considering the step response. Now let's go and try to implement this in Java. And in our demo integral project, we already have this memoized integral that takes care of memoization. Note that the default number of points is 100. And what we are going to do is I'm going to create another class called low pass filter, for example. Let's have a main method here, and so what I'm going to do, I'm going to create a function that represents the low pass system. So function or integral function 1D G, or impulse response or impulse new, or here. So T goes to what? So we have to have a kind of like an if statement here. So t goes to if t is less than 0, we're going to return 0. So if or we can use the t less than 0, we're going to return 0, else we're going to return math dot basically xpov minus t over tau. Okay, and now double tau, let's say 1 second, so the units are second. All right, and this is our impulse response. If t is less than 0, we return 0, otherwise we return, and we can even plot this. So MATLAB chart, fig, new MATLAB chart, fig that, so double time is math utils dot linspace from 0 to 100 seconds with 1000 points, and double y, for example, is array func dot apply, t goes to impulse dot value at t, we're going to apply to time array, and fig dot plot time y, fig dot render, fig dot show. All right, so I should also multiply this exponential by tau, and let's go and remove this check. Okay, so as you can see, tau times minus t over tau, and okay, so it returns 0, so let's go minus 5, for example, to 100. It's just okay, so oh sorry, this should be the value at t, not tau. Okay, so this is our impulse response, and the reason that we're not getting 1 because our resolution is not good, so maybe let's just go 1 to 50, minus 5 to 50, 10,000. Okay, so this is our impulse response. Okay, and as you can see, this tau, if you're familiar with this linear system, tau represents the width of this pulse. So at 1 second we are about half, more than half. The width of this small pulse reduces. Okay, so this is our impulse response, and then we create an integral function 1D input is t goes to if t less than 0, we return 0, else we return 1. So our input is a step, let's call it a step input. All right, and I can also plot that y input, let's just call it input, and then we want to plot it, input with the color red, for example. Okay, not the input, we have to have a step input here. Okay, okay, let's see. Oh, okay, so why do we have this error here? All right, so we have this. Okay, so the red is the input, which is a step, and the blue is the characteristic of our system, which is the impulse response of the system. Now the output is basically the convolution of these two things. So we're going to have use a memorize integral object. Okay, and so we're going to create an integral function 1D, and convolution function t goes to t goes to what? T goes to t goes to, actually we shouldn't do this. So what we want to do, we want to create a function and we want to pass in. So first of all, we can directly test the step response, and in the step response we know that we just have to integrate over the impulse response. So let's go and do create a memorized integral out step, new memorized integral. Our function is basically impulse, start is -5 and end is 50. All right, and for this function we set the number of points to 10,000, and then out step calculate. Okay, we do the calculate and we come here and we plot, let's say with green, from out step dot get points, which are the time stamps, and out step dot get results. Okay, so this green. So as you can see, what happens here is that as we expect, we get some sort of rise time, and eventually the response, this green one, which is the output, reaches the steady state, which is basically the output becomes equal to the input 1, but with some sort of rise time, this exponential rising of the function, right? And that's the main characteristic of the step response of a low-pass filter when we calculate the convolution. Now this gives us a very exact and stable result for the output because we're using memorization, so it's pretty fast and pretty accurate, and even if we increase the number of points here, it doesn't really change the efficiency that much. It's still pretty fast, okay, and pretty accurate. So memorization is a great technique when you want to deal with these linear systems, and this topic we will come back to this topic of linear systems and try to study them in very much details. Okay, now what if I want to calculate the implement the generalized version of convolution. So what we can do is, let's say, for convolution, what we need to do, and we want to use this memoized integral, right? And this memoized integral requires an basically integral function, right? And this integral function so we can write this down out a step like convolution. And what we are going to do here, this impulse, basically the output is a function, the input. Remember, this memoization technique, what it does is it calculates a function of t, okay, of a function f. When we're dealing with convolution, basically what happens here is that remember, because the signal is 0 before time 0 and the impulse response is also 0 before time 0, what happens is that the boundaries of the integration always go from 0 because of this g to t because of this one, right? So it always goes from 0 to t, and we are here basically, okay? But then the problem here is that there is a t also inside this integral function. How do we deal with that? So we're integrating 0 to t of f of t minus y gy dy, right? And the way that the question is, can we just use this simple memoization object to do that? So this should be y, right? And this should go to like the for example, step input dot value at t minus y times the impulse, for example, value impulse dot value at y, right? But then we have this problem of t here, so I guess we cannot just directly use this memoized integral to deal with the fact that there is also a t variable inside, right? So what we can do is we probably can update this such that the memoization works for an integral of a to t for a function of f of x and t, okay? So t could also be inside the integration, and the way we are going to do it, maybe we can just so if we pass in an integral function 1d, then we can assume that the input function is not dependent of t. If we pass an integral function 2d, okay, then we can assume that this function also has a dependence of t, right? So func, and let's call this let's refactor rename it func 1d, and let's create a function 2d, func 2d, and what we're going to do here, we're going to basically let's see, we're going to assign the func 2d here, and func 1d is null, So then in the calculate we can check. So we're passing in a func 1D, and if the func 1D is not null, which means we already passed this integral 1D object, so the assumption here is that then the function that we are integrating over is not dependent of the t variable. But if func 1D is null, it means that we have supplied a func 2D, so it already also depends on t, right? And what we can do then is to think about which variable, the first variable or the second variable, is the t or the x. Okay, one of them is x, the other one is t. And what we are going to do here is that we're going to assume that the second variable, so here we're going to assume that f is f of x and t, and here we're going to assume that our function f is just f of x. So no dependence on t, no dependence on t. This has in fact dependence on t, okay? Because when we're calculating the integral, it's actually important to know that, okay? The convolution t actually appears in the inside the integral as well, and that's the main thing. And then when we come to memorization, when we're calculating the integral, we say that basically our x goes to basically we can just test. So this is func 1D, and if func 1D is not null, which means we have set the func 1D, and we assume that it doesn't depend on t, and else if func 2D is not null, it means that actually the func 2D has been set, and our integrand, the function f, depends on t, and t is the second variable, okay? So, but the problem is that we cannot pass in a func 2D, right, in the integral 1D. So we say that, okay, we are integrating over x, func 2D value, and the first variable is x, the second variable is t, and remember t is basically our points, right, that we are integrating, and at each step we are passing calculating from 0 to t2, okay? And here this integral 1D, so we have to calculate at t, and so this should be t2, right? Because in each step the result is the result of integration from start to t2, okay? And this looks good. And the initial condition is that, okay, from start to start is always 0, right? So we just put 0 in. Alright, so let's test our previous case. Okay, still works. And let's try to implement it using a 2D implementation here. Let's say we want to pass in x and t, pass in a 2D function, 2D integral function. it goes to impulse at basically value, and just x, right? So what happens here is that our integrand does not depend on t, but we're using the second construct. So let's see if this works. Yeah, so it still works. Okay, exactly the same result, but using a 2D integral function, which does not depend on the second variable, which is the t, the output variable. All right, so we have this. Now let's try to implement the general convolution. The general convolution, we pass in a y and t to the integral function, and then the step input. Let's call this just the input. So let's refactor rename it. It's just the input, and we calculate the input. Oh, okay, so we had this input, let's call this just, I don't know, x. Okay, and then let's do the so this is the convolution, and input value t minus y times impulse at y. All right, so everything is correct. Let's call it out, or just the convolution. So this is a more general case. We're still calculating the step response, but we are using the convolution. Okay, and let's see, why do we have an error here? Oh, okay, so we have to also do the convolution, set the number of points 10,000, and convolution dot calculate. Okay, and result. Yeah, exactly the same result. But then the thing is that now we can calculate the response to the time response to any input, not just the step. So let me just add some parameters here. After rendering the plot, let's say fig.x label time second, and y label fig.y label function, and okay, let's run this again. And I'm going to just plot the result of the convolution. And let's copy this and put it in our slides. All right, or maybe let's reduce the interval. So instead of having -5 to 50, let's go -5 to 10, for example. Let's plot it with a blue color. All right, fast configure. Let's copy it and paste it. here, for example, and let's put the response on top of it. Okay, so this is our time response, okay, a step response. And what is important here is that so the other thing is that instead of copying, I can save it as a PDF file, and when I go to my PowerPoint, I can directly import the PDF file, so it has a higher resolution, higher quality. All right. So what's important here now? Let's look at other things. Instead of having the step response, let's look at, for example, okay, let's bring this back. This is green. But instead of having a step input, let's go and do something more interesting. So let's say for t less than 0, it's 0. For t greater than 0, let's say we have t, a linear ramp. Okay, this is a ramp input. The input is a ramp function, and we want to calculate the output from -5 to 50. And so the blue one is the step response, the red one is the input, which is the ramp, and the green one is basically the response. Let me just double check. So input t minus y, and impulse at y, yes, and then we are calculating the convolution from -5 to 50. Input t minus y, and then output impulse dot y. Yeah, looks correct. And let's say this is, for example, math dot sine of t. So we have a sinusoidal with frequency of 1 Hertz. And so so again the output is something like this. So let's reduce the frequency. The green one is the output. Okay, this was an interesting topic about how to efficiently calculate a function over a long interval using memoization. I hope you enjoyed this, and I'll see you in the next video.